Hello friends, in this video I'd like to solve the following problem from the Romanian International Mathematical Olympiad Team Selection Test 1998, problem 14. We want to find all functions u from the set of real numbers into itself, for which there is a strictly monotonic function f, such that f of x plus y equals f of x times u of y plus f of y for all real numbers x and y. So it's a very nice problem from Romania. Here are my hints. First, notice the symmetry of the left-hand side of our equation and use it. And remember that since u is strictly monotonic, it's not constantly zero. It's what I'm saying. F of some argument is for sure not zero. And use the previous two facts to express f of u of x in terms of f of x. And now the fun part begins. You will have two cases. One is easy, when u is constant, and the second one, much more interesting, when u is not constant, try to reduce our original functional equation to the Cauchy functional equation. And remember this very powerful fact that if some monotonic function g, monotonic, very important, if some monotonic function g satisfies Cauchy functional equation, that is g of x plus y equals g of x plus g of y, then our function must be linear. So g of x equals b times x for some constant b. So give this problem a try and I will see you in just a minute. Alright, so let's take our very first equation and notice that f of x plus y is f of x times u of y plus f of y. But this expression right here is symmetric with respect to x and y. So in essence, we can change x and y. So f of y times u of x plus f of x equals the same expression. Alright, and now I will do some shuffling. First, I will put this expression on the left-hand side and this on the right-hand side. And we will have f of y u of x minus f of y equals f of x u of y minus f of x, which allows me to write the following after factorization: f of y u of x minus 1 equals f of x u of y minus 1. Alright, now we can almost find u of x, but it needs division by f of y. But there is potentially a problem with division by 0. But notice that since f is strictly monotonic, since this is strictly monotonic, f of y0 is for sure not 0 for some argument, or some y0. And that allows us to conclude that u of x equals 1 plus, let's write u of y0 minus 1 over f of y0 times f of x. I have divided by this and I have added 1 to both sides. But really, this part right here, y0 is a constant, so this part is also a constant. i.e. u of x equals 1 plus some constant times f of x, where c is a constant. Alright, and now I will set this function back in our original equation. So equation asterisk becomes On the left-hand side, we have f of x plus y, and on the right-hand side, we have f of x times u of y, but instead of u of y, we can put 1 plus c times f of y plus f of y. And that means that f of x plus y equals c times f of x, f of y, plus f of x plus f of y. Very nice. And now our reasoning will break into two separate cases, depending on the fact if c is 0 or non-zero. Case number 1 will be easier, so let's start with it. Case number 1, when c is 0. Well, then f of x plus y equals f of x plus f of y, and this is exactly Cauchy functional equation. So f satisfies Cauchy functional equation. And remember that f is strictly monotonic, and maybe let's write it, and f is strictly monotonic. So in this case, f of x must be equal a times x. And moreover, since it's strictly monotonic, where a is some constant, but it is not 0. Alright, so if c equals 0, maybe let's write it in full. In this case, u of x equals just 1, and f of x is any linear function, non-constant. Right, this case was easier. Second case, harder. Case number 2. Case number 2, when c is not 0. Well, let's call that this equation right here, let's call it triangle. And now I will manipulate triangle to get some new form of equation. So our equation triangle becomes, or is equivalent to saying, well, f of x plus y equals c times f of x, f of y plus f of x plus f of y. In essence, I wish to reduce this equation also to the Cauchy functional equation, but it needs some work. First, I will start by multiplying both sides by c. So we have c times f of x plus y equals c, maybe let's write it, it's c times f of x, c times f of y, plus c times f of x, plus c times f of y. And now I will do one more thing. I will add 1 to both sides. So it's c times f of x plus y plus 1 equals c times f of x, c times f of y, plus c times f of x, plus c times f of y, plus 1. And now you need to notice one fact, that the left-hand side can stay as it is, and the right-hand side can be factorized. It's c times f of x plus 1 times c times f of y plus 1. Alright, so maybe, you know what, let's, for the sake of brevity, let's call this new function g of x. So let g of x be equal to c times f of x plus 1. And notice that since f is strictly monotonic, And since C is non-zero, G is also strictly monotonic. We'll use it later. Now I need a new page, so give me a minute. All right. Now, let's put, yes, so we have defined g of x to be this. So our equation becomes g of x plus y equals g of x, g of y. It's almost Cauchy functional equation, but not quite, because we need addition on the right hand side, and now we have multiplication. How can we deal with it? Well, by taking a natural log, for example. But we must be sure that both sides are actually positive. How can we be sure? Well, let's call this condition square. So set, for example, y to be equal x, then, well, g of 2 times x is g of x squared, which is obviously greater than or equal 0. But to take natural log, we must eliminate the possibility of being 0. And to do that, notice that if, for example, if g of some number is 0, or some real number y0, then set y to be y0, and we have the following: g of x plus y0 equals g of x, g of y0, and g of y0 is 0, which means that g is constant, which cannot be, because we have demonstrated that it is strictly monotonic, contrary to the fact that g is strictly monotonic. So that cannot be. So in other words, combining this condition with this observation that g of y0 cannot be 0, now we see that for every real number x, g of x is actually strictly greater than 0. Alright. And now I will take this, I will take natural log on both sides of my equation square. So taking natural log on both sides of our condition square, and we have the following: natural log of g of x plus y equals natural log of g of x plus natural log of g of y, because of well-known properties of logarithms. And now let's call, so let h of x, another function, h of x, let it be equal natural log of g of x for all real number x. Well, remember that our function g was strictly monotonic, natural log is increasing, so h is also strictly monotonic. Since g is strictly monotonic, h must also be strictly monotonic. Moreover, moreover, our function h satisfies Cauchy functional equation. Yes, h of x plus y equals h of x plus h of y. So since h is strictly monotonic, and h satisfies a Cauchy functional equation, h must be linear, i.e. h of x, or maybe let's write it in gold, h of x equals b times x, where obviously b cannot be 0 because it's strictly monotonic. Alright, and now let's go back. H of x was natural log of g of x. Yes, it was natural log of g of x. So, natural log of g of x equals b times x. So, g of x equals e to the power b times x. Alright? Or we can make a substitution right now. Let's define a to be e to the power of b. And we see that g of x actually equals a to the power of x. And notice that b was not 0, so a is not 1. A is not 1. Alright, but what was g of h? Let's take a look. G of h is c times f of x plus 1. So c times f of x plus 1 equals a to the power of x. And f of x equals a to the power of x minus 1 over c. Over c. Very well, and now what was u of x? Well, u of x was c times f of x plus 1, so it is just a of x. A of x. Alright, so in this case, we have the following. Yes, so where a is some positive number not equal 1, also let's write it, because a was e to the power of b, so not only a is not 1, but it's also greater than 0. And moreover, c is non-zero. So here we have exponential functions, but also, if we go back, there was a special case where u was equal 1. And we are in our problem statement, if we go back, we wish to find all functions u for which function f exists. So every exponential function u is good, and also function which is constantly 1 is also good. So maybe to finish our problem, let's call this condition Roman 1. Let's call this condition Roman 2, and by Roman 1 and Roman 2, u of x can be any function a to the power of x, where a is any positive number. It can be 1, because 1 of x is just 1, and it was covered by case Roman 1. And that is our answer. Our solutions are just exponential functions and function which is constantly 1. Thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.